A video monitor is a major part of any microcomputer system, providing the user with information from the computer's processing unit in easily understandable graphic or alphabetic forms. To the computer user, a monitor is an essential interfacing tool. To the computer technician, however, a monitor can be an unwelcome guest in the service center. Based on analog techniques more often found in television circuitry, video systems are a bit of a mystery to many digital technicians. In this training package, we will discuss the basic operating principles of the video monitor, as well as monitor alignment techniques. Before viewing this tape, you must read the video monitor's theory and alignment workbook and complete the review questions in it. The material in this tape demonstrates many of the concepts found in the workbook. Refer to the workbook if you have questions or want more information on the subjects covered in this tape. In this package, we will examine and discuss standalone monitors, but most of the information is valid for monitors that are part of an integrated computer unit. Let's start our discussion of monitors with a look at some of the major parts found in them. A CRT, or cathode ray tube, is the basis of the video monitor. Inside of it, an electron gun generates a beam of electrons that strike the luminescent faceplate, forming tiny dots of light. These dots make up the alphanumeric and graphics data that we see on the screen. There are several external parts of the CRT that you will need to recognize. The first of these is the face. This is the part of the CRT on which the data is displayed. The inside of this surface is coated with phosphor, a material that glows when struck by the electron beam. Monochrome CRTs have a smooth coating of a single type of phosphor. The type of phosphor used determines the color of the screen and its persistence, or how long it glows after being struck. Color monitors use three types of phosphor arranged in groups called trios. Each type of phosphor glows in one of the primary additive colors, red, green, and blue. There are also 3 electron guns in a color tube, one for each color. A thin grid of material called a shadow mask is placed between the guns and the phosphor to reduce interaction between the colors. A tension band helps prevent the CRT from spraying glass forward in case of an implosion and is epoxied to the rest of the tube. Do not attempt to remove or tamper with the tension band. It may spring off with great force and will leave the CRT unit less safe from implosion. The bell of the tube is the large curved area behind the face and tension band. The depression in the side of the bell is called the high voltage anode and provides connection to a coating inside of the bell called the aquadag. The outside of the bell area is covered with a conductive coating called the dag. The dag and the aquadag form a huge capacitor which provides a steady supply of between 11 and 30,000 volts to attract electrons to the CRT's faceplate. The thin area towards the rear of the tube is called the neck. The electron gun is inside this area of the CRT. Although it looks like a convenient handle, never pick up a tube by the neck. This can breach the tube's sealed environment, resulting in an astonishing and dangerous implosion. The nipple is a small protrusion of glass at the rear of the tube, surrounded by the CRT's connecting pins. Cutting the nipple off of a tube disarms it by letting air trickle in. No presentation on cathode ray tubes is complete without a discussion of safety. There are 3 basic hazards in dealing with CRTs: implosion, high voltage, and poison. Implosion occurs when air rushes into the tube's sealed environment. The glass exterior will shatter, sending fragments flying for quite a distance. To avoid imploding a tube, follow these precautions. Always store and transport CRTs in their original packing. Take care not to drop CRTs. Do not store them on high shelves or transport them without securing them. Whenever you dispose of a tube, first disarm it by cutting the nipple. If possible, place the tube in its packing carton beforehand. If packing is not available, use a sturdy, deep wastebasket. Do not assume that a CRT with a cut nipple is immediately safe. Allow at least a minute for the pressure to equalize. Another problem that you may encounter with a CRT is lead poisoning. The inside of the faceplate is coated lightly with lead to protect against X-ray emissions. The lead and possibly also the phosphor itself are toxic. If a CRT were to break, the lead-coated glass could poison anyone that it cut or contaminate the environment. For this reason, it is illegal in some states to put a CRT in the trash. Check local regulations before throwing them away, and be extremely careful if cleaning up a broken tube. Finally, you must exercise caution when handling CRTs due to the high voltages present on it. Remove any jewelry before servicing a CRT to prevent accidental contact with the high voltage points. Be careful not to touch the anode or anode lead. For maximum safety during service, keep one hand in your pocket or behind your back to avoid completing a current path through your body. Even when the CRT is not installed in a monitor, it still presents a shock hazard. The DAG and aquadag of the tube form a very large capacitor, which is not automatically discharged on power off. A CRT can store a high charge for a very long time. Always discharge a CRT before handling in order to reduce the danger of shock. The correct way to do this is to connect a 10K resistor in series with a clip lead and connect one end of the clip lead to the ground. The resistor will help prevent arcing during the discharge. Connect the other end of the resistor to an insulated screwdriver and carefully insert the blade under the cup of the anode lead. Be sure that you are not touching the screwdriver blade with any part of your body. Use one hand to handle the screwdriver and place the other hand in your pocket. This completes our description of a CRT. Remember, the major external parts are the face, the tension band, the bell, the DAG, the neck, and the nipple. Also remember to handle CRTs carefully. Discharge all tubes before handling. Store them in their original packing. Disarm all tubes by cutting the nipple before disposal. During service, be sure not to touch the anode or anode lead. The other major component of a monitor is the video driver circuitry, which serves three main purposes. First, it produces the high voltage signals necessary to drive the electron beam around the face of the CRT. The horizontal and vertical sync signals from the computer synchronize the travel of the beam with the video information. Next, it produces the several high voltages needed to bias the CRT's elements so that they can produce an electron beam to illuminate the phosphor. Finally, it amplifies and conditions the video signal from the computer so that it can turn the electron beam on and off. In standalone monitors, there must also be a power supply circuit to provide input voltage to the other three sections. In integrated computer monitor units, the video driver is usually fed by the main system power supply. In some units, all the video driver circuitry is on a single board. In others, it is divided among several PCBs. In either case, there are several major components you must recognize. The input connector brings video and control signals from the computer into the video driver circuitry. There are several types of input connector that you may encounter. A composite video connector brings all of the signals that the monitor needs on a single pin: horizontal sync, vertical sync, video information, and, in the case of the color monitor, color burst, all pass to the monitor through a single RCA jack. The composite connector is the same for color and monochrome systems. The other two main types of video input, direct and RGB, both use a DB9 connector. This is a bit misleading since their pinouts are somewhat different. RGB inputs are used only by color monitors. This scheme uses 3 pins numbered 3, 4, and 5 for video information. Each one represents one of the primary colors, red, green, and blue. Direct drive monochrome inputs accept video on a different pin, number 7. Pins 3, 4, and 5 are unused in this layout. Because of the different configuration, RGB color video boards will not work with monochrome monitors and vice versa. Video generator circuits designed to work with either monitor type will generally have switches or jumpers to select color or monochrome mode. If you do not select the correct setting, no video will be displayed on the monitor. Regardless of the connector type, the monitor will use the information from the computer's video circuit in the same way. One of the major functions of the driver board is to produce horizontal and vertical sweep signals which drive an electromagnetic yoke, causing the electron beam to move around the screen. The sweep circuitry usually contains several adjustable components that allow you to align the monitor for a stable, correctly centered and sized display. Adjustable coils are used for some of these alignments, and variable resistors, sometimes called pots, for others. Potentiometers are also sometimes used to adjust power supply outputs of standalone monitors. Speaking of sweeps and power supplies, The horizontal sweep circuitry generates some very high voltages. The horizontal output transistor produces retrace pulses of up to 1000 volts in some monitors. Be careful not to touch this component during service. Most monitors use the output of the horizontal circuit to do more than drive the horizontal yoke. The pulses are applied to a flyback transformer, which produces extremely high voltage, low current supplies needed to bias the CRT elements. As with the horizontal output transistor, do not touch the flyback while servicing the unit. In addition to these important components on the driver board, there are some peripheral parts of a monitor that you will need to recognize. One of these is the yoke assembly. As we mentioned before, the output of the sweep circuits induce magnetic fields in the yoke, causing the beam to move around the face of the CRT. The yoke rests on the outside of the tube where the neck widens into the bell. It is important to orient the yoke correctly. If you do not, the display area will be slanted or, in extreme cases, upside down. Remember that high voltage spikes pass through the yoke. Be careful not to touch the windings during service. Mounted on or near the yoke assembly, you will find some magnets. Some of these, found in all types of monitors, adjust the shape and position of the display area. Color monitors have additional magnets that are used to adjust the 3-electron guns so that each beam strikes only the proper color phosphor within the correct group. A final important peripheral part found in color monitors is the automatic degaussing coil. This looks like several strands of wire wrapped around the outside of the CRT. A current passes through these wires on power-up, hopefully removing any residual magnetism from the shadow mask. Occasionally, the tube may still need to be manually degaussed. Before completing our tour of the video monitor, we must discuss a few general service precautions. As with all computer equipment, connect the monitor to an isolation transformer before attempting to service the unit. This precludes the possibility of mismatched grounds and accompanying damage to the monitor, test equipment, and most important, the technician. Remember, a variable transformer or variac does not provide isolation. Do not use a variac in place of an isolation transformer. If you need a variac, use both. When servicing a monitor, there are a number of things you must not touch. These include the anode and anode lead, which develop a DC voltage of several thousand volts. The yoke coils and the horizontal output transistor, which may produce as much as 1000 volts, and any large capacitors on the board should be avoided as well. Also, discharge the CRT and any high voltage capacitors before doing any soldering, resistance measurements, or other handling of the internal parts of the monitor. When replacing parts in a monitor, take note of the way the parts are shown on the schematic. Parts inside a gray shaded area are critical for X-ray protection, over voltage protection, or other safety-related reasons. If they are so labeled, use only exact replacement parts so that the monitor remains safe to use. This concludes our discussion of the physical layout of the video monitor. Keep the locations of the major components, and even more important, the safety precautions in mind as we continue through this tape. One of the most common service procedures that you will perform on monitors is alignment. Proper alignment corrects problems such as an unstable or misplaced display, incorrect colors, and occasionally no video at all. There are several alignments that are found on almost all monitors, color and monochrome alike. You must perform these alignments in a specific order because each one builds on the one before. In this tape, we will describe a general order of alignments, but always consult the manual for specific instructions on any monitor. Also, if one alignment is grossly incorrect, you may want to rough it in before beginning the regular alignment procedure. Before beginning a monitor alignment, let the unit warm up for about 15 minutes. This will allow the various components to reach a stable operating temperature before you start. The power supplies in many standalone monitors produce an adjustable output voltage. Always make this adjustment first, since the power applied to the various sections of the circuit affects their alignment. Next, align the horizontal sweep circuit, since power to the CRT itself is usually derived from the horizontal output. There are three possible adjustments to this circuit: sync, size, and linearity. Perform the sync adjustment first. It sets the frequency of the oscillator for a stable display. Next, adjust the horizontal size, which aligns the oscillator's duty cycle. Make the linearity adjustment last, as it fine-tunes the oscillator output waveform. Once the horizontal adjustments are complete, move on to the vertical sweep circuit. When it is also correctly aligned, you will have a clear, stable display, which makes it much easier to perform the rest of the alignments. Perform the vertical adjustments in the same order as the horizontal: sync, size, and then linearity. Once again, we first set the frequency, then the duty cycle, and finally touch it up with the linearity control. Before completing the sweep adjustments, turn the monitor on and off several times and check for a stable display. Also, make sure that the alignment is good both when the unit is cold and warm. It is possible to set the sweep adjustments just within the capture range of the oscillators, which will cause the monitor to sync properly at times and to roll or jitter at others. Now that we have a stable, correctly sized display, we can move on to the tube bias adjustments. Most monitors have external brightness and contrast controls, which allow the user to set the screen to a comfortable viewing level. There are also internal adjustments which limit the range of brightness that the customer can select from, and we will set these next. Set the internal brightness first. This adjustment is also called the sub-brightness alignment. It may vary the cathode voltage or the bias of the output transistors. Align it so that the customer can select any brightness level from black to very bright with the external brightness control. After the sub-brightness level is set, you may move on to the focus adjustment. This adjusts the voltage on the focusing element so that the electron beam converges right at the faceplate, producing small, sharp pixels. A misadjusted focus control results in large splotchy areas on the screen. Always perform the focus adjustment after the brightness, since changing the level on the acceleration grid affects the beam's convergence point. Once you have completed all of these electrical alignments, you will need to make several mechanical adjustments. First, make sure that the display area is not tilted either to the right or left by moving the yoke around the neck of the CRT. This is called the Raster tilt adjustment. Next, you must center the display area in the middle of the physical area of the screen using the centering magnets located on the yoke. Once this is done, perform the Raster geometry adjustment. This consists of turning small magnets located on posts to obtain a square screen that does not bulge out or dip in. Bulging is also called barreling, and dipping is called pin cushioning. Consider this adjustment as magnetic fine-tuning, and as always, perform it last. In addition to the adjustments found on all monitor types, there is a series of adjustments that are peculiar to color monitors. Like the alignments just described, there is a specific order in which they must be performed, since they tend to interact with one another. When aligning a color monitor, perform all of the adjustments that we have already discussed before beginning the color adjustments. This assures that you will have a clear, stable display, which will make the color adjustments much easier. The first two alignments that you will perform involve adjusting magnets to control the positions at which the electron beams strike the faceplate. Remember that color monitors produce 3 electron beams, each assigned to one of the 3 colors of phosphor on the faceplate. In a correctly aligned color monitor, each beam strikes only its assigned color of phosphor, and all 3 beams strike phosphors within the same group or trio. The purpose of the magnetic color adjustments is to see that this actually happens. The purity adjustment assures that each electron beam strikes only its own color of phosphor. If the purity is misadjusted, a full screen of a solid color will be tinged with some other color. This alignment needs to be done first because you cannot bring the other adjustments into specifications on a monitor with misadjusted purity. Once the purity adjustment is complete, you must perform the convergence adjustment. This assures that all 3 beams are striking phosphors within the same trio. If this adjustment is incorrect, the edge of each white area of the screen will have a border of 1 or more colors. Colors that require more than one gun to be on will also show incorrectly colored fringes. There are 2 parts of the convergence alignment. One, called static convergence, affects the center area of the screen and is performed by adjusting 2 sets of magnets. Dynamic convergence, on the other hand, affects only the edges of the screen and is done by adjusting the position of the yoke itself. Once these adjustments are complete, the CRT is capable of producing proper colors over the entire display area. Next, the video driver outputs must be adjusted to produce true colors throughout the brightness range. The adjustments that do this are collectively called grayscale, or black and white tracking adjustments. There are two separate parts to the procedure. The first is called the cutoff or bias adjustment. This assures that all three colors of phosphor fade to black at the same level of input drive. This adjustment is necessary because the different colors of phosphor require different amounts of current to cause them to glow. If the cutoff point is not correctly set, the monitor will not fade smoothly from white to gray to black as the brightness is turned down, but rather appear to change colors. Once the cutoff alignment is done, the drive or color temperature adjustment must be made. This procedure varies the drive to each of the three video outputs separately so that all three phosphor colors glow with the same level of brightness. If this adjustment is not done correctly, a supposedly white screen will appear to be somewhat blue, pink, or green. You must sometimes consult with the customer before finalizing this adjustment. What appears to you to be pure white may not look good to him. Once you have finished all of these alignments, the monitor's picture will be clear, sharp, and properly tinted. Remember to perform them in the correct order, since they interact with one another. Now that we have discussed video monitor alignments in a general way, let's see how they are actually done on typical monochrome and color monitors. We will begin by aligning this composite monochrome monitor. First, remove all jewelry and place an isolation transformer in the monitor's AC input path. Connect the monitor to a computer's video output and boot a diagnostics diskette. Select a video alignments program. We will use this software to generate the patterns needed for the alignment. Consult the service manual before beginning any alignments. The adjustment points, and in some cases the procedure, will vary for different models. As we discussed before, we will adjust the power supply voltage first, since it affects the operation of the rest of the monitor's circuitry. Select a program option that will produce a full bright screen and rotate the brightness and contrast controls to obtain the brightest possible pattern. These two steps produce maximum current draw so that we can adjust the power supply under maximum load. Connect a voltmeter to the test point specified in the manual. Be sure that it is set to read DC volts and that the voltage range is higher than the specified power supply voltage. Select your ground point carefully. In many monitor power supplies, the chassis is not an appropriate ground for the primary side of the power supply. Using an improper ground point can result in a misadjusted power supply and also in damage to the driver board components in the monitors with hot chassis. Once the meter reading is stable, use a non-metallic alignment tool to bring the voltage into the specified range. In this case, the plastic tool serves two purposes. One is that it prevents adding capacitance to the circuit being adjusted, which can distort circuit output. In the monitor environment, it also protects you from shock if you accidentally drag the alignment tool across a high voltage point. Once the power supply output is correct, move on to the sweep adjustments. Different manufacturers recommend different patterns to use for these adjustments, each of which has advantages and disadvantages. Use the pattern specified in the manual or as close to it as you can easily produce. Adjust the horizontal sweep circuit first, since it may provide bias for the vertical section. If this circuit is not set correctly, the screen may jitter from side to side, be too wide or narrow, or perhaps the characters may not all be the same width. The first adjustment in this series is horizontal sync. If the monitor has an external horizontal hold adjustment, set it to the center of its range. Adjust the internal horizontal sync control until the display is stable and the edges of the display are straight. Next, adjust the horizontal width control until the display area's horizontal measurement matches that described in the manual. If the unit you are servicing has a horizontal linearity control, use it to make sure that the characters remain the same width across the screen. A full screen of capital H's is a good pattern to check this with. Once these alignments are complete, move on to the vertical sweep settings. If these are incorrect, the screen may roll, appear too tall or short, or the characters may not all be the same height. As with the horizontal sweep, begin with sync adjustment. Set the external vertical hold control to mid-range and adjust the internal vertical sweep or deflection control until the display is stable. Once this is done, adjust the vertical size, then linearity. These two adjustments interact, so you may need to go back and forth between them. Before leaving the sweep adjustments, turn the monitor on and off several times and make sure that the display always powers up stable. It is possible to set the horizontal or vertical oscillator right at the edge of its capture range so that it sometimes locks to sync input but other times does not. If this happens, readjust the sweep sections until you get a stable picture at all times. This will prevent intermittent heat or stress-related sync problems. Now that we have a stable display, we can move on to the tube bias adjustments. The first of these is the internal or sub-brightness control. This adjustment varies widely from one monitor type to another. In this unit, it is done in two parts. First, we set the external brightness control to its maximum level and then remove video input. Next, we adjust one of the sub-brightness potentiometers until the raster is just visible. This is the maximum brightness level that the user will be able to select. Next, reconnect the video, select a full white screen, and set external brightness to minimum. Then we adjust another internal control until video is just barely visible. This is the lowest brightness level the user can obtain. These adjustments allow the user a wide range of brightness levels without wasting any external adjustment range on levels that are always black or that always show a raster. Once brightness is set, move on to the focus adjustment. Set the external contrast and brightness to maximum, since focus is poorest when the screen is bright. Select a diagnostic option that places characters on the screen and adjust the focus control until the dots and lines of the characters are as sharp and as small as possible, both at the center and in the corners of the screen. Once the focus is correct, we have completed all of the electronic adjustments of a monochrome monitor. However, there are still a few mechanical alignments that we must do. The first of these is the raster tilt adjustment, which makes sure that the display area is perpendicular to the face of the screen. To make this adjustment, first select a crosshatch pattern. Loosen the screw that holds the yoke to the neck of the CRT and rotate the yoke around the neck until the picture is straight up and down. This process orients the yoke so that the magnetic fields that it produces drive the beam directly across or down the screen. Be careful not to touch the yoke wires during this process. Next, center the display area on the face of the CRT by moving the centering magnets on the yoke housing in relation to one another or rotating both of them around the neck of the tube. These magnets will deflect the electron beam slightly, causing the display to move around on the face of the CRT. Finally, check the screen for any pin cushioning or dipping inwards on the sides, and for barreling or bulging outwards. If either of these conditions exists, rotate the raster geometry magnets until the display area is exactly rectangular. This completes the alignment procedures for a monochrome monitor. Many of these same adjustments are present on color monitors, and they are done in the same way, so we will not repeat them. There are, however, some adjustments peculiar to color monitors, and we will discuss them next. When aligning a color monitor, follow the same safety precautions that you use with a monochrome set. Remove all jewelry, use an isolation transformer, and do not touch any of the high voltage components. Color monitors contain most of the same controls that monochrome units do, such as power supply, sweep, and focus adjustments. Do these before beginning the color alignments. It is also a good idea to degauss the unit before beginning the color alignments. This will reduce the effect of residual magnetism on the alignment. To manually degauss a monitor, first turn it on. Then plug in the degaussing coil and turn it on while standing about 6 feet away from the monitor. As you walk towards the unit, circle the coil in front of the tube. The screen will appear to run and change color due to the effects of the coil. Once you have passed the degaussing coil in front of the entire CRT, move the coil around both sides and the top of the screen. Then back away from the unit. Do not turn the coil off until you are about 6 feet away. Once this is done, you may begin the color alignments. The first one is called the purity adjustment. Here you use magnets to align the electron beams so that each beam strikes only one color of phosphor. You will need a full red screen and later green and blue screens for this adjustment. One way to obtain these displays is to override the blanking circuitry of the monitor and turn the bias of the appropriate electron gun all the way up while turning the other two down. This results in one gun remaining on at all times, which produces a full, solid color screen. If you use this method, mark the bias potentiometers before moving them so that you can return them to their original positions. Although this is the method described in most manuals, there is a simpler way for the shop technician to produce solid color screens. Our video alignment diagnostics contain an option to produce a full screen of white, blue, green, or red. This method requires the use of a computer, while the first method does not, but it eliminates changing the beam bias, which is really nothing more than intentionally misaligning the set. In either case, once you have a full green screen, you can proceed with the purity alignment. Loosen the yoke clamping screw and pull the yoke as far back on the neck of the tube as possible. You may turn the monitor off while you do this if you like. Locate the two purity magnets behind the yoke. They're the pair with the tabs marked P. Bring the two purity tabs together and move them to the side of the CRT. Now turn the monitor back on and observe the screen. You will need to be able to watch the screen and move the magnets at the same time, so you have two choices. One is to stand in front of the monitor and wrap your arms around it to reach the magnets. This is workable if awkward, but be careful not to touch the yoke or other high voltage components. A less acrobatic alternative is to place a mirror in front of the CRT and to stand behind the monitor, observing the screen in the mirror while manipulating the magnets. Once you are in position, move the purity tabs apart and around the yoke to obtain the widest area of pure green in the center of the screen. There will always be a yellowish-red tint at the sides since the yoke is out of position. Push the yoke forward into its normal position and the reddish tinge should disappear. If it does not, pull the yoke back and repeat the alignment. Once you have a pure green screen, check the purity of the red and blue guns in the same manner and align them if necessary. When all colors are pure, retighten the yoke. If you obtained your colored screens by adjusting the gun biases, you must now reset them to their original positions. The next set of alignments that you must perform are called convergence. These make sure that the three electron beams are striking phosphors right next to one another, so that turning all beams on produces a solid white dot rather than a red dot, a blue dot, and a green dot. The first adjustment, called static convergence, operates on the center area of the screen. To make this adjustment, you move the other two sets of magnets behind the yoke. One of these sets of magnets is labeled with the number 4. These are the 4-pole magnets, and they bring the red and blue beams together to produce magenta. The 6-pole magnets are labeled with a 6 and converge the green beam with the red and blue. To begin this adjustment, select the dots option from your video alignment program. This will produce several small dots scattered about the screen. Turn the intensity control down until the screen is dim but still readable to reduce the effects of varying beam drive on the adjustment. Look closely at the dot at the center of the screen. If the monitor is properly converged, the dot will be solid white. If the convergence is off, there will be a fringe of color around the dot. In extreme cases, you may actually see 3 dots, one of each color. Sometimes it's easiest to make this adjustment by first making it as bad as possible. Move the 4 and 6-pole magnets until there are 3 separate dots. Next, looking at the dot in the center of the screen, move the 4-pole magnet tabs only until the red and blue dots converge into a magenta dot. Make sure that the dot is as close to pure magenta as possible with no fringe of red or blue. Once this is done, converge the magenta dot over the green dot by moving the 6-pole magnets in relation to the 4-pole magnets. You may also move the 4-pole magnets around the CRT neck, but do not change their relative positions because that will misalign the red and blue beams. When these alignments are properly done, the dots near the center of the screen will be pure white. Those on the edges may still show a border of other colors. As an additional check of the static convergence, select a crosshatch video pattern from your diagnostics. Make sure the lines are pure white near the center of the screen. If there are red or blue fringes on the vertical lines, rotate the individual 4-pole tabs until they disappear. If there is a red or blue border on the horizontal lines near the center, move the 4-pole magnets around the yoke, preserving the spacing between them until the lines are pure white. If there is a green border on the center lines, use the 6-pole magnets to correct it. Move the individual tabs to remove vertical green lines, and move the 2 tabs together to be rid of green horizontal lines. Do not attempt to adjust the lines or dots near the edges of the screen using this procedure. Static convergence is effective only at the center of the screen. Once the area in the middle of the display is converged, move on to the dynamic convergence adjustments. Select a crosshatch pattern from your video diagnostics and observe the areas at the corners of the screen. Chances are there will be some divergence of the colors here. It is almost impossible to avoid. To minimize the divergence, you will move the plastic wedges that are inserted between the edge of the yoke and the CRT. This will change the tilt of the yoke in relation to the tube, reducing the convergence errors caused by the beams not striking the faceplate squarely near the edges. If the lines of unwanted color appear to cross, that is, if there is a band of one color on the left side of the vertical line at the top of the screen, and a band of the same color on the right side at the bottom, tilt the yoke up and down to minimize the crossing. This works whether the beams are crossing on a horizontal or vertical plane. When the crossing near the corners is minimal, insert the bottom wedge and one of the top wedges to secure the yoke's vertical position. Next, see if any of the beams appear offset from the others in the corners of the screen. If so, tilt the yoke from left to right to minimize the offset. When the edges of the display are as close to pure white as possible, insert the final top wedge to secure the yoke. You may need to change the position or depth at which the wedges are inserted to obtain the best convergence. This is the last of the magnetic color adjustments. Recheck the purity and raster tilt adjustments if necessary before moving on to the electrical alignments. The electrical color alignments are collectively called black and white tracking or grayscale. Essentially, these adjustments attempt to electrically compensate for the differences in the 3 types of phosphor on the faceplate. First, we will adjust the cutoff or bias control, which alters the bias of the output transistors so that all 3 phosphors cease to glow at the same input level. If all 3 channels were driven at exactly the same level, the red phosphor would continue to glow at levels where the green and blue had already faded to black. This means that the color on the screen would appear to change as the intensity changed. The screen might fade down to pink rather than gray as the brightness or contrast was reduced. To adjust cutoff, you will need to obtain a full white screen or a thin white line in the center of the screen. Then set brightness and contrast to mid-range. Usually you will remove the internal drive controls from the circuit, either by shorting them out or removing a service switch or jumper. This will prevent the drive control settings from affecting the cutoff adjustment. Consult the manual for exact directions. Turn all 3 cutoff or bias potentiometers all the way counterclockwise. This will result in a black screen. Next, turn the red bias potentiometer back up until a medium brightness red pattern appears. We start with the red beam since it requires the most current to turn on and will match the other 2 beams to it. By starting with a medium bright red beam, we are setting all 3 output transistors near the center of their bias range, which will produce the best results. Mark the position of the screen control, which is often mounted on the flyback transformer, and turn it down until the screen is black. Then turn it back up until a very faint trace appears. Once the red trace is as dim as possible, turn the green bias control up until the red trace becomes a dim yellow. Then turn up the blue bias until the trace becomes a dim white or gray. When you are satisfied with the color of the display, re-enable the drive controls and turn the screen grid back to the mark. The video should now be normal brightness. The color may change as the brightness comes up, but the drive adjustment will correct that. At this point, you can proceed to the drive or color temperature adjustment. This involves reducing the gain of the red and blue output transistors so that they only cause red and blue phosphors to glow as brightly as the green phosphor does when it is driven full strength. As you can tell from the description above, each color of phosphor has a different degree of luminescence or brightness, and the green phosphor is the dimmest of all. If all 3 phosphors were allowed to glow as brightly as possible, the color balance would be incorrect. To complicate matters still more, the human eye is not equally as sensitive to all colors of light. Objectively, we could make each phosphor produce exactly the same amount of light. However, the color still might not look exactly right. When we adjust the drive current, we are aligning the three output transistors so that subjectively the screen appears white when all three guns are on. Turn the contrast and brightness controls fully clockwise or until the screen is as bright as possible, and select a full white screen from your diagnostics. Using a white piece of paper, determine if the display is pure white or if it is tinged with red, green, or blue. If the screen appears too red or green, turn down the drive adjustment potentiometer for that color until the display is pure white. If the screen appears too green, you will have to turn the blue and red drive controls up. There is no green adjustment control. As we discussed earlier, green is the dimmest phosphor and is normally driven full strength. If you have trouble getting the display exactly paper white, err on the side of a little too blue. Operators generally find a blue screen less objectionable than a pink or a pale green one. When the display is as nearly white as possible, start turning the brightness and contrast controls down. Make sure that the screen remains white throughout the entire range of brightness. If the color is off when the brightness is low, the cutoff controls may need fine-tuning. If problems occur when the brightness is high, the drive controls need work. Before closing up the monitor, check the display with red, green, and blue screens, with dots, crosshatch patterns, and with text. If any of these show problems, repeat the alignment procedures. If you follow these procedures carefully, the monitor will produce clear, correctly colored video. However, in monitor alignments, as in all things, the customer's opinion is the one that counts. If he thinks that your perfectly aligned monitor is a little too pink, readjust it for him. This concludes our presentation on video monitor alignments. If you have questions, reread the video monitor's theory and alignment workbook or consult the manual for the specific monitor you are working on.